Good afternoon, everyone. I am Praveen Timilsina, and this is the presentation for the paper titled Study of Such Phenomena in a Hydropower Plant, a Numerical Approach. This is the outline of this presentation. First of all, we'll discuss about the introduction of the topic, what SARS is, where it is used, and why it must be used. Then we'll talk about a few published literature of SARS and our objectives for the study. After that, the methodology of the study will be discussed with all the steps taken in modeling and simulation of the phenomena. Finally, the results obtained are discussed and conclusions are drawn towards the end of the presentation. Now, moving towards the topic, we can define surge tank as a very important component of hydropower, which is designed to protect the conduit system or the piping system from high internal pressures which appear during rapid closure and opening of valves. We can see on the right hand side of the slide, the surge tanks are situated at the end of the headrest tunnel before the penstock pipes. The first figure has a simple surge tank, whereas the second figure has an orifice, so it's called restricted orifice surge tank. Now the main function of surge tank is to shorten the distance between the turbine inlet where the valve is and the nearest free water surface. By this, it dampens the pressure fluctuations during rapid opening and closing of valves. When the valves are closed, the water level in the chamber rises, absorbing the surplus kinetic energy. But in case of opening of valves, the chamber acts as a reservoir which will provide sufficient water to pick up the new load safely and quickly. The picture alongside shows the surge tank and switch yard structure of Anku Khola hydropower in Dhading district. Lots of research works have been done in such system because of its importance in hydropower. One of the very first study was done by Sima et al. In 1958 AD, in which they studied the role of orifice in surge tank by carrying out experiments and comparing theoretical and experimental water hammer waves. Similarly, Mogaddam in 2004 derived a general solution for the oscillations in simple surge tank in terms of non-dimensional parameters. Nabi and his team analyzed the hydraulic design of surge tanks of two potential sites in Pakistan and recommended the suitable designs. Also, studies have been done by various researchers implementing different methods to optimize the design of surge tank and observe the effects of various parameters like cross-sectional area and friction losses. From the literature study, it was found that substantial amount of work has been done in the analytical calculations and numerical study of surge behavior in the hydropower. A few studies have also been done with CFD analysis, particularly with commercial CFD codes like ANSYS CFX. Nepal, having an enormous potential for hydropower, has a lot of scope for the study of such surge tanks in different potential sites. Hence, the main objective of this study was to develop a methodology to perform hydraulic simulations of surge tank using an open source CFD toolbox, OpenFOAM. Also, our specific objectives included observing the flow behavior during valve closure and opening, and also comparing the differences between simple surge tank and restricted orifice surge tank using OpenFOAM. The following flowchart shows the general method followed for this study. Each of these will be described in the coming slides. Geometry. A 3D geometry of the whole water transportation system, including headrest tunnel and penstock pipe, was prepared in SolidWorks. For approximating the diameter of the surge tank, we use the Thoma criterion for stability with a factor of safety of 2. The approximated diameter was used to aid surge to the prepared 3D geometry, and altogether we prepared 3 geometries, one without surge and the other 2 with simple and restricted orifice surge. Then we did analytical calculation for the first upsurge, assuming in case of U-tube oscillation using this formula. The positive sign gives the maximum upsurge and the negative sign gives the maximum downsurge. This formulation neglected the presence of penstock and assumed instantaneous opening and closure. The value obtained was 18.68 meters, which must be more than the real values because of the assumptions. The meshing of the geometry was done by using Snappy HexMesh utility of OpenFOAM, which uses the STL files of the geometry from SolidWorks and conforms the mesh to the surface. The two-phase physics of such case with water and air was solved using Interfoam, which is an OpenFOAM solver that solves the fluid problem with two incompressible, isothermal and immiscible fluids using a volume of fluid based multi-phase approach. K omega SSC turbulence model has been used with reference to literature, and density, kinematic viscosity, and surface tension coefficient of air and water were defined for temperature of 20 degrees Celsius. And all the simulations were performed in the presence of gravity of 9.81 meter per second square. The boundaries in the computational domain are inlet, opening, outlet, and valves. The upstream end of the headrest tunnel was treated as inlet patch. The upper end of the surge tank was named opening. Similarly, the inlet to the turbine or the end of the penstock pipe was named as outlet, and all the walls of the headrest tunnel, surge shaft, and penstock pipes are named as valves. The inlet patch is given a total pressure condition representing the head of the reservoir from the tunnel inlet. The opening patch is given a zero pressure atmospheric opening condition. The outlet patch was given a variable flow rate boundary condition where the flow rate of water changes with time corresponding to the closing and opening of valves. The walls are treated as rigid and are given a no slip boundary condition but without friction to simplify the case. With these boundary conditions and physical parameters set up, we performed different simulation to observe the flow in the surge tank. This graph shows the general behavior during the opening and closing of the valve. When the outlet mass flow rate changes, the inlet flow rate undergoes damped oscillation to reach a steady value matching the outlet value. The first simulation was performed with simple surge without orifice with instantaneous opening and closure in order to compare with the previously calculated analytical value. The results of the simulation gave maximum downsurge height of 11.398 meters during opening and maximum upsurge height of 11.045 meters during closing. These values are less than the analytically calculated upsurge and downsurge height value as required. After that, time of opening was increased to 30 seconds and time of closing was increased to 6 seconds and results were observed and compared. This graph shows the time development of inlet flow rates with the defined outlet flow rate. It was observed that inlet flow rate is almost similar to outlet flow rate when there is no surge, which is justified since there cannot be any void inside the domain. However, when surge was provided at the end of the headrest tunnel, the oscillations started appearing in the values of inlet flow rates as discussed in the previous slide. It was also observed that the oscillations are dampened out faster in case of surge tanks with orifice. In these two graphs, the mass oscillation effect in the surge shaft during opening and closing of the valves are shown separately. The use of orifice creates a clear distinction in the oscillation and as it restricts the flow of water in and out. The maximum upsurge in the surge shaft is reduced from 10.799 meters to 7.943 meters with the use of the orifice. These two graphs show the pressure at a point in the headrest tunnel exactly under the surge shaft. It was observed that in case of pipe flow without surge, the pressure change at the point during opening and closing is discrete rather than continuous and higher than cases with surge. When there is a surge in the domain, it was noticed that the pressure change is oscillatory but smoother. Actually, this is how surge shaft protect the penstock pipes from pressure pulse by dampening the pressure waves. And the orifice had a similar effect, faster dampening of pulses. Like pressure and mass flow rates, when surge is in use, the velocity in the headrest tunnel also changes suddenly during opening and closing. It is the reason of water hammering in pipe flows. In the cases with surge, there is smoother oscillatory transition of velocity to the steady state value. With orifice, the velocity reaches the steady state value faster than with simple surge tank. After the analysis of obtained values, the flow visualization was done using ParaView. Here, figure A shows the velocity vector plot when the gate is opening. It can be seen in figure A that the water in the headrest tunnel hasn't gained any velocity, although the gate is already partially opened. So the water flows down from the surge shaft to maintain the flow. Similarly, figure B shows the velocity vector plot when the gate had just closed. It can be seen that the water in the headrest tunnel still poses velocity, so the water enters into the surge shaft. This is how surge shaft absorbs the sulfur's kinetic energy. The effect of restriction created by orifice can be clearly seen in these plots. This way, orifice dampens the oscillation quickly. Now these graphs show the water volume fraction plot showing the maximum upsurge and maximum downsurge in cases with simple surge and restricted orifice surge tank. The values for maximum upsurge and downsurge were less in case of orifice than with simple surge. Finally, in conclusion, in this paper we performed a numerical study of surge phenomena using open source CFD code OpenFOAM. The effect of using surge tank is studied with a simplified 3D geometry identical to a Nepalese hydropower plant. The diameter of surge tank was calculated using Thoma stability criterion and an analytical solution was obtained for the maximum possible upsurge or downsurge. The corresponding values obtained with numerical analysis in OpenFOAM were less than the analytical value due to the considerations of penstock length. Then, numerical simulations were performed in OpenFOAM by increasing the time of opening to 30 seconds and time of closure to 6 seconds. The increased time of closure and opening showed reduced values of mass oscillations, observed height, and pressure fluctuations. Also, the cases without surge, with simple surge, and with restricted orifice surge were compared. And this study lays a foundation for the future research on numerical analysis of surge phenomena in a hydropower using OpenFOAM. Also, the methodology applied in this study can be implemented in commercial projects to validate the design with open source free CFD code. These are the references we have used for this study and in this presentation. Now, before ending my presentation, on behalf of the authors of this paper, I would like to acknowledge Kathmandu University Supercomputer Center for supporting this research by providing the computational resources. And special thanks to Dr. Rajendra Adhikari, Assistant Professor, Kathmandu University, for helping us with the use of supercomputer for OpenFOAM. Thank you.